I got the cue. I got the cue. You guys hear me?
Yeah, okay.
Yeah.
With one hand.
I,
So you have the chat and you have the queue.
no, I've got the questions for the queue. I can do that. The chat I can't
Okay.
type. I got one hand.
And
But
how many
there's quite
volumes did you take?
none. I haven't. I'm no opiates today. I'm going cold turkey.
Yeah, really? Okay. So we check
It's
when you
2 days is enough.
whether you still
Um,
conscious, whether you fall over or not.
yeah, you
Okay.
got to put your face to the mic. I can't hear you when you're that far away.
We'll check regularly with you whether you're still conscious or you just faded out, man, and fell off the chair.
Good.
Okay.
Yeah, I need a button, a release button. If I pass out and drop the button, you'll know. There's just questions already about remote control of the slides. I mean, the PDFs are up there. I know there's two different buttons on allowing either they control it or you control it. It's not obvious which is which, but either way, they don't do remote slide and screen sharing. You've got the slides. They either hit the button or you hit the button for them. Correct? Do you know which
Well,
button to hit, Tony?
we'll see with the first preso. The API, the tooling seems to have changed. So we figure out as we go, man.
Yeah, it changes every time. I believe in you, Tony.
You have to dial in this chair as well.
Something here? Or?
No, that's just a cue.
Okay, okay. Knopje dan net.
So why it doesn't even open power for me? All right, now I have this thing. Okay, folks, we're about to start.
Muting.
So, you in? You try to get in, huh? Yeah, normal stuff. Yeah. So what's this new document API? I thought now I just click on the press, it shows up, but does it look like that at all?
That gives you the list of the materials. You can just select them from there.
Yeah, that's what I did. Meeting materials, right?
Yep. Mm-hmm.
All right, so now I click on the stuff. The stuff tries to download it. And then what do I do from here? I can't present it.
Show of hands. Sure you can.
That's what I thought.
Presentation.
It downloads it. Oh, folks. So now I do share screen or what?
New screen's been shared. Yeah, there you go.
Except I somehow have to get the material. I thought it was supposed to do all this stuff automatically.
You have to share it and you have to accept it. And then you could pass the control by going the little revoke screen icon by you. Put your mouse over that, and it shows you where you can after you either slide control or you pass the slide control to them.
No, the only thing that allows you is to share screen. That's about it. Oh man, all these improvements every time, no? Yeah, so when I do presentation view, how the hell do I put material in here? So what's the tooling now?
Well, you have no presentation up yet. There you go.
Right. Okay, so welcome, starting beer session. We have a semi-conscious chair online. So Greg will be managing the queue. We have a prodigal son that came back. Bravo. I start sharing. We have one of the fathers came back. A pretty good agenda today, a couple of interesting things. Yeah, let's start.
Can I add a note? I want to add a note about the queue. The queue is a composite of people online and in the room, and to manage the queue properly, everyone should be using the tool. So even if you're in the room, get on Meet Echo, and as you come into the mic, hit the queue button so we can manage the queue order based on who hit it first, both in the room and online.
Right, so everybody has to basically dial in and mute their laptop and, jump on
Correct.
the queue. Otherwise, we'll be standing by the mic. New procedures. All right, note taker. One after another. Don't fall over. Here you are.
I can do the.
Ice.
Okay.
Ice been promoted to note taking. Hey, Sandy.
Okay. S is better than me. For no, thank
Ice,
you.
Ice will do it. Much simpler here in the room. There is a note taking tool, right? When you did you manage to dial in? Ice doesn't have Wi-Fi, so that sucks. So we only have one laptop with material. The other one has only the queue. All right, how do we note taking now in this degraded environment?
Old-fashioned.
Oh, old-fashioned sucks. Give it another shot. What do you get in?
Yeah, he can type it remote, but he won't have the notes from the people online to read if he can't get into Meet Echo.
Right, because people like to run with us while we're taking notes.
Yeah. So we need to find someone who's in the 21st century.
115 without anything. Try the traditional. Try the IETF hotel. And try the traditional without anything. Yeah, the unprotected one. No, there's one which is completely unprotected, like legacy. There's one which is completely open. Yeah, legacy. Nobody does legacy except me and Ice, so that's why it works. All right, so let's see what Ice gets the note taking. All right, so let's start. So I'll be flipping those things, and then we'll see how the stuff works. New tooling, fine. The usual note well. Plus, everybody please wears mask. Yeah, we should pretty compliant, except some people snacking. Snacking is limited to 60 seconds, okay? And if it's not, it will be next IETF, I'm sure. All right, so everybody please sign in. Tooling changed again, hurrah, okay? And please mute your microphone because otherwise, we'll have looping effects. The agenda is Meet Echo. I don't even know whether we're running Meet Echo anymore. Anybody willing to do the Meet Echo stuff? I thought so. No, so we have note taking, and we'll have the recording. All right.
Anyone doing the notes should be in Meet Echo and composite voices at the mic, as well as people who are typing online. So we do Meet Echo. Anyone doing notes has got to be on it.
I lost you, Greg. So the notes are automatically going on Meet Echo or not?
It will be recorded, but what's said at the mic won't be. So if someone can type them in, that's the point of having a note taker to put it all together.
Right, exactly. So the note should encompass, of course, the whole questions on the mic. All right.
Yep.
We're not having any technical issues. Otherwise, you know what to report them. Good. So agenda, a bunch of updates on the previous stuff, a very interesting conversation on efficient P4-based beer implementation. Looks actually fascinating on the Tofino. And then Toles is showing something towards recursive beat masks, which looked like a pretty crowded presso. We see what comes out of it. Then probably an FRR update and TE extension by Sandy if we find time. Okay. So, what's the status? So, the TE stuff is an RFC. Congratulations, Toles. Yeah, you know, claim to fame. Beer bar APA passed and got an RFC. So now we have. Yeah.
Room applause.
Room applause. Yeah, come on, come on. We don't get that many of those. We need, you know, cheap wins. The beer bar IPA is also RFC now, so we have a clean architecture, you know, either run to it IGP or otherwise do our own things if necessary.
Clap, clap.
So thanks for Jeffrey to actually herding that one along for quite a long time. All right, now comes the public castigate. The OSPV 3 stuff is being not taken care of. I was twice on people. I was promised updates. Updates not delivered. One of the co-authors is sitting here and looked properly bedraggled, right? So, gentlemen, I give you last warning and 2 weeks. And otherwise, I start to go look for another shepherd. Waimo did shepherding, but the stuff as far as he's not addressed. So I give you 2 weeks for a version that takes care of the stuff. Otherwise, you know, you lose the opportunity for eternal fame. And I will go and drag another author and make him editor and basically start, you know, to get the stuff delivered. So once again, last call, but in a different sense. Bunch of things are moving forward, nothing particular here. Bunch waiting for Shepherd. Yeah, nothing very interesting here. Unless somebody wants to come. Yeah, Andrew? Yeah, so that just kicked in. So I have to go and look at this draft and see whether in a state we need to actually call early review. So the early reviews will be coming now much faster than before, right?
We didn't hear Andrew remote. Can all questions go to the mic, please?
Yeah, to the mic, please. Yeah, right. And then you can basically.
Yeah, Andrew here. I don't know whether this has been circulated to all the working groups, but we've got a policy in routing area now that before drafts go to the area directors after last call, they must have gone through an early review through the directorate. This is just to help us speed along the pipeline, etc., you know, because it's a lot easier if we get documents that have been reviewed. So I was just reminding the chairs about that with the number of documents that are looking like they're about to arrive. Yeah.
Put this kind of stuff in relatively fast. We just need to prove that it has been mentioned and the mic is taken care of. It doesn't have to be like a verbatim stuff. Okay. All right. So, so we need a bunch of shepherds for you know, early reviews, so people can clean the stuff up before we push it further. List extensive, FRR surely interesting. Everything else, multicast as a service probably interesting. TE, no opinion. The beer.
We got a question at the mic.
One.
Greg.
Okay, Greg Mirsky Erickson. Sorry to be pain in the butt.
No, it's just you.
Oh, you. Okay, okay. Then should I assume that everybody enjoys it? Okay,
yeah,
fine.
All right, so go on.
Okay, I'm glad to. So, beer ping. Beer ping in last call. We received Shepherd's review. Thank you for the Shepherd. Worked on the addressing. I submitted my proposal to the pen holder and never heard since. So the draft expired.
Who is the pen holder editor on it?
An agenda.
Of official editor or just the first author?
He's first author.
Right.
So I would appreciate if chairs can think of assigning the editor to the draft so we can move on. Because the problem is, not the problem is, as additional, as you listed BFD draft here, so that ping, the BFD and path MTU discovery depend on progress of beer ping.
No problem. Please send official request to the list. The chairs will turn around, give the first auto 20 minutes time to react, and if not, we basically assign an editor to progress. Yeah,
we've reached out to Nahendra already. We got some response, but nothing really progressed. I think it's fair enough that we just move the pen.
Yep.
Yeah, actually, in for fairness, I send the request before the meeting.
Yep. Absolutely.
Fair enough.
Request has been sent. Let's move the pen.
Yeah, we give it some time and then we move the pen. You know, we get an editor, so we move the stuff forward. Okay. Anything else on the drafts outstanding on the status? Jeffrey on the queue.
Oh, that's Jeffrey. Sorry.
Yeah, Jeffrey from Juniper. I think there is one draft missing here, probably because it's expired and it's my fault. It's the beer proxy draft. We believe it's ready for last call. I will refresh it and then.
Refresh. We need the shepherd and so on, and then we have to call it for the last call. Whatever. Next time. Next guy on the mic, please. No acrobatic. You know, throwing around and juggling things. Okay. So that's it. Next one. You do the notes, okay? So I run the slides. So, Human?
Well, first thing first, Ice, welcome back. Thank you. Maybe we can get some Belgian beer now, man. So with that said, if I knew the last call was as easy as going to the microphone, I wouldn't have wasted anybody's time with going over this draft again. But I think we tried to do 3 last calls on this, and I think it went to the working group too. I don't know what was, I think, you know, they were in favor of pushing it through. So I don't know, do you want me to go through it, or this is a question for chairs?
What's quickly in the room?
Sorry, what was the answer?
Let's see if you can step through, or we have time.
Yeah, I mean, I don't want to waste anybody's time if everybody knows about the draft and, you know, we're going to just do a last call on it, you know, get a shepherd on it, then, you know, I can give 10 minutes back to the working group.
Show of hands. People need refresh, then we run 5 minutes. Nobody gets hurt. Okay, 1, 2, yeah, please run a refresh.
All right, sounds good.
Keep it snappy, but at least people know what the whole thing is about. Thanks.
I'll make it very snappy. So the problem we are trying to solve is that some providers that they are trying to go, next slide, please, actually. Some providers that are trying to go to the next technology, which is beer for multicast, they want to replace some parts of their network. So they buy brand new hardware that is beer capable, and they want to replace one portion of the network. As an example, in this case, the network is being multicast LDP, MLDP, and a small island within that network is going to get upgraded and to beer. And with this draft, basically what they can do is they can, I wouldn't use the term stitch, they can signal the MLDP through the beer core from one island, MLDP island, to another MLDP island that is connected through this beer core. So next slide, please. So basically the way it's done is like PIM signaling. All that happens is that when MLDP effects arrive at a beer edge router, we grab that MLDP FEC and the MLDP signaling, if you will, and we use RFC 7060 and we shoot it from the let me get my terminology right, the downstream beer router, which is ingress beer router, I guess, to the upstream beer router. And the upstream beer router keeps track of all these downstream routers, if you will, that are interested in building this multicast tree via the MLDP signaling. So the upstream beer router, edge router, builds a table or something similar to a table that tracks all the downstream routers that are interested in the tree. Next slide, please. So obviously, when you get into the other side of the MLDP to the other MLDP island, then your FEC just goes all the way to the source via MLDP signaling, and then your signaling is fully achieved at this point, and then your data path starts. Data path starts from the source via MLDP, via LDP MPLS in-cap. And when it goes to the beer domain, we have a list of the downstream routers that are interested into that tree, and we generate a beer header that has the bets of all the downstream routers in the beer header, and we shoot the packet all the way through the beer core to the downstream LDP island. We remove the beer header, and then we go to the wild via the MPLS header itself. And that's how the solution works. So it's not really a stitching, it's just tunneling it. And yeah.
Okay, last call request. Should we do show of hands or take it to the list, Greg? Faded out. Okay, so we issue a last call on the list, okay? Unless there's any questions. We have time for a question or two. Queue empty. Okay, next one, thank you. BRBGP Jeffrey, who is doing that?
Next time.
All right, so this is an update on this BGP extension for beer signaling on behalf of the co-authors. Next slide, please. There's a bit of history on this draft. It had passed working group last call before, and I was the shepherd. I did the review. I had some comments. Then the main authors had lost steam, so they couldn't address the comments. And additionally, it was only intended to for this BGP DC scenario, with BGP being the underlay. And it is assumed that all the routers would support beer. And if there is one router that does not support beer, then the ingress replication will happen all the way to the BFERs. This is a problem that was pointed out in another draft, the multicast as a service, and it has also has a solution for that situation. After considering all the factors like nobody was actually working on comments, and then we have this problem, so we decided to do a revamp. So I joined as the editor. We moved the solution from the multicast as a service draft into this base one so that it can handle generic situations, and not just for the BGP DC and where all the routers support beer. Next slide, please.
Sorry, one too many.
Yeah. So this is an example of what I was talking about. Here we have the BFR1 on the left side. There is a non-BFR in the middle, which does not support beer, and then followed by BFR2, and then BFER 1, 2, 3 on the right side. before this new revision, all the BFRs or BFERs, they will only advertise their own beer prefixes and their encapsulation information. Now, when BFR calculates the BIF entries for BFR ER123, the next hop in the BGP advertisement is that non-BFR. And it has no idea that BFR is also in the, BFR2 is in the pass. So it will just tunnel the traffic to BFER123 directly. If it had known that BFR2 can be used, then it could have just tunneled to the BFR2 only. With the new approach, all the BFRs, beer router, when they re-advertise the beer prefixes, they will update the beer information, and they will also update a next hop sub TLV in the beer TLV to themselves. So this has two purposes. The main purpose is that in this example, BFR2, when it re-advertises the BFER123 prefixes, it updates next hop to itself. So now when BFR1 gets that, it sees the next hop is BFR2, and it has the encapsulation information and associated with BFR2. So it knows that for all those BFER123, they can just be reached from BFR2. So that handles the non-BFR case very well. Another side benefit is that all those beer prefixes, they are now re-advertised by the BFR2 with the same beer TLV that allows the better BGP and ROI packing. So next slide, please. The procedures is basically what I just talked about. Next slide. There is another enhancement here. We just talked about that. Let's go back to that picture. So here, BFER123 originated their NRI for their beer prefixes, and then it is assumed that everyone just re-advertised them everywhere. But there may be situations where you do not want to re-advertise the beer prefixes everywhere. For example, BFR2 can say that I'm not going to re-advertise those BFER123 prefixes. Instead, BFR2 will just advertise its own beer prefixes, but it uses sub-TLV that is defined in the other draft, beer prefix excuse me, re-advertisement, that in that new sub-TLV, you will just list all the BFR IDs reachable from this BFR. So that's what I was talking about on that slide later. Let's go back to that slide. Yeah. So summary of all the changes in this revision. We extended the scope for general applicability. It also handles MPLS and non-MPLS encapsulation, handles non-BFR. We updated the signaling so that the transit BFRs do not need to advertise the beer information with their own beer prefix anymore, unless they want to use the proxy range sub-TLV to advertise BFR IDs that are reachable from them. We also added a section about the BIF calculation, updated text for how to handle those beer information and TLVs at the beer domain boundary. Next slide. So with these changes, we need to do another round of working group last call. We also need a new shepherd. I was the shepherd before, but now I'm joined as an auditor. Oh, by the way, Sandy joined as a contributor. She helped a lot in, especially on that proxy range sub-TLV support. Yeah.
Questions on the queue? Nothing? In my opinion, this needs to be bounds of IDR as well. Very significant change of procedure. Okay, and now because you carry the stuff transitive through, I would like to have these guys a look in terms of like atomic attributes, aggregates, blah, blah, right? You're triggering a couple of procedures. So I will fire something towards the IDR and then we see whether anything pops up on the list and then fine, we issue a work group, last call again, and Shepherd, please, if anyone volunteers to do that stuff. Okay, done. Next one. I think Jeffrey, you know. Prefix. Okay.
Yeah. So this is the updates on the beer prefix redistributes drafts on behalf of the co-authors. Next slide, please. Just a quick review. We have three IGP domains in this topology, even though they are running three different IGP instances. The beer subdomain itself is actually just a single one. They cover all those the domains. Question is, how do we redistribute the beer information between them? That's one question. Another question is that if we are using BGP-LU, because with BGP-LU, the prefix for edge routers are typically not distributed into IGP. They only advertised by BGP among those border routers. So in that case, how are we going to do beer forwarding? So the approach there is to have the border routers advertise their own beer prefixes with that same proxy range sub-TLV I mentioned earlier to list the external BFR IDs that are reachable by them. So that's the basic idea on how to handle the BGP-LU case. That's basically what this draft is about. It's been there for quite some time. I will not get into the details. The purpose of this presentation here is just give a quick overview and then request for working group last call. Next slide. Yeah, that's it.
Okay, so the prefix redistribute. Last call, Shepherd. Huh? Okay. Thanks. Questions? No one on the queue? Thanks.
We got last call, show of hands in the room.
Should we do it or just issue to the list?
No, we do it in the room, and we have a tool that does that. This was which draft again? It vanished. What was the title of the draft?
That's the prefix redistribute.
Prefix redist. Okay.
Yeah. If you want, actually,
all right.
The
show of hands.
We do the virtual tool, right?
Yeah, this just gets everybody remote and in the room. So we have a count, we have a record, and we take it to the list. $15 with 16. No dissent. Room's up. I said we got it. All right. And 17, 18. More people are coming in. 19. One person says it's not ready, and they change their vote back to 19. Looks unanimous. All right. Thanks, room. We'll take it to the list. Ending session.
So let's also do a show of hand for the BGP last call, but I would wait until we get this IDR feedback, and then I would only go for the last call, maybe next meeting.
But we should check the room.
Okay.
All right. Show of hands. We have someone at the mic. Oh, he vanished. All right. Unanimous, no dissent. All right, thanks everyone. We'll take that to the list. Oh, another one came in. We're at 15. We're there. All right. Ending count.
Okay, so it looks like the
back to the agenda.
Okay, so it looks like the BGP is going last call as well, while I make the IDR, basically checking with the IDR, what you call it, integrated part of the last call. Okay. There was someone on the mic?
They vanished.
Good. Okay. So
no, Human's up. Human's up.
Do we want to do the same thing for the LDP one?
True. If we're consistent,
sure.
we're consistent. Okay. Let's run the MLDP.
All right. That was MLDP, correct?
Yeah.
I just have to put a title in it. All right. Show of hands in the tool. Thanks, Human. No dissent. We're at 15, 16. Looks like we got full support. All right, thanks everyone. We'll take you to the list. Ending count.
Okay, Stefan, kannst anfangen. Besten Dank für die Präsentation. Und jetzt fallen wir zurück in die barbarische englische Sprache. All right, next one. So, Stefan, this looks actually like a very interesting presentation, especially for implementers or people pouring this stuff into silicon or even, very efficient software. Okay, let's go. We don't hear you. No, if you on the tool, you have to open the mic, Stefan.
So you can hear me, right? Okay, because I cannot hear you,
like you were
then I will just
power bar
go over the presentation without hearing you. Okay, can I start? Okay, perfect. Hello, everyone. My name is Stefan Lindner. I'm a PhD student at the University of Tübingen. And today I'm going to talk about an efficient P4-based BIER implementation on Tofino. And this is joint work with my colleagues Daniel Merling and Michael Metz. Next slide, please. Okay, I'm going to start my talk with a short recap what we did before in previous work. Then I'm going to talk about the problem statement and the implementation of efficient BIER in P4. And finally, I'm going to talk about an optimization that can be applied to this implementation. Next slide, please. Okay, so at IETF115, we already presented the first implementation of BIER and BIER fast zeroed in P4 for the Intel Tofino. And there we used an iterative processing approach where in each iteration, one next hop was served. So we receive a BIER packet. In the first pipeline iteration, we forward the packet to the first next hop of the BIER packet. Then we clone the packet, recirculate it. In the second iteration, the second next hop is served, and so on. Next slide, please. This approach has one huge drawback because we make heavy use of recirculation. And recirculation requires capacity on the switch. So for example, when we get 100 gigabit per second multicast traffic with 5 next hops, then this results in 400 gigabit per second recirculation traffic that needs to be processed on the switch. And when we look at the chart here on the left side, and when we get 100 gigabit per second traffic, have only a single recirculation port, and want to send the packet to 3 next hops, this is the green bar, then we only achieve around 40 gigabit per second because the pipeline is overloaded due to recirculation, so we have heavy packet loss. We were able to solve this issue by adding dedicated recirculation ports to increase the recirculation capacity. So with 3 recirculation ports on the right side of the plot, we are able to serve up to 4 next hops at line rate with 100 gigabit per second. However, these dedicated recirculation ports are physical ports of the device, so these cannot be used for any other traffic than recirculated beer traffic. Next slide, please. So our goal is, or was, to reduce the recirculations, to improve the efficiency, and to save capacity on the switch for other traffic. And a simple idea that one can come up with is that we want to determine all max stops of the beer packet in possibly one shot, and then use, for example, a static internal multicast group to replicate the packets to the required max stops in one shot, so that we do not need recirculation. Well, this idea has some challenges in P4 and on the Intertofino, because with beer bit strings with at least 256 bits, it's quite difficult to map this bit string to the set of a packet's next stop in a single table lookup when we do not have specialized hardware as when we just have an Intertofino. And a second challenge is that we only have a limited number of configurable static multicast groups, so we cannot simply have any combination of possible next stops as multicast group because it's just too much. So the question is now, how can we do this more efficiently? Next slide, please. Next slide, please. Just as a very small recap, P4 is a high-level programming language to describe data planes. And there we have a compiler that maps the P4 program onto programmable pipelines of targets, for example, in our case, the Intertofino. Next slide, please. So our approach for a more efficient beer implementation is now the following. We have a switch with a certain number of ports, for example, 32. And now we divide all ports of that switch in k so-called configured port clusters. For example, the first 10 ports are the first configured port cluster here with the yellow border. Another 10 ports are the second here with the blue border. And the remaining 12 ports are another configured port cluster. These configured port clusters can be overlapping, so they do not have to be disjoint. And of course, ports within a configured port cluster do not have to be physically next to each other. This is just for simplicity. And all configured port clusters together have to cover all ports of the switch. And now we want to determine which configured port clusters require a packet copy. So we get a beer packet that, for example, should be sent through the first port of the switch and through the last one. So we need the first configured port cluster and the third configured port cluster. And this may be done again, possibly iteratively. However, only with a few iterations, like 1 to 4, and not like 1 to 32 as in our previous implementation. And when we now know that, for example, C1 needs a packet copy, we can use a suitable static multicast group to replicate the packet to all required next stops within this configured port cluster, but only towards the required next stops. And with this approach, we need a maximum number of k-1 recirculations for k configured port clusters. So for example, with a 32 port switch and 3 configured port clusters of size 11, 11, and 10, then we need at most 2 recirculations independent on the number of next stops. And in our last implementation, this was next stops -1. So this is a drastic reduction in the number of recirculations. Next slide, please. And the question is now, okay, how can we determine which configured port clusters need a packet? To that end, we look at all combinations of these configured port clusters here called SI. With our example with 3 configured port clusters, we have 7 combinations, the single configured port clusters, all combinations of 2, and all combinations of 3. And then we look at the so-called combined FBM, which indicates all BFERs that are reachable through the subset. When we look at a port of the switch, then this port is used to reach certain BFERs, so this port has an FBM. Likewise, when we look at the configured port cluster, it contains ports, so all ports together build also the FBM of the configured port cluster. And when we now have a subset of configured port cluster, we just bitwise OR the individual FBMs of the configured port clusters. And when we now receive a beer bit string, which is here shown in the example, with BFERs that are reachable through the first configured port cluster here in orange, and for example, the second configured port cluster here in blue, then we apply a ternary match operation. A ternary match is simply a bitwise AND operation, and we do it with the complement of the combined FBM, and we define a match when the result is 0. What does this mean? This means that the complement of the CFBM has a 0 at every bit position where the beer bit string has an activated bit. And this means that the combined FBM has a 1 at every bit position where the beer bit string has also an activated bit, which simply means that the CFBM serves all BFERs of the beer packet. In this example, this would be the case for S4 and S7, because these two contain the first and second configured port cluster. However, S7 also contains the third. We do not want to send a replication to the third configured port cluster because it doesn't need a packet. Luckily, when we order this table according to the size of the subset, then we get as first match the smallest combination that is required. And then in this case, this is S4. And then we can simply select the first configured port cluster for further processing. Then we recirculate, and in the second step, we can work with the remaining configured port clusters that need a packet copy. Next slide, please. And now that we know which configured port clusters need a packet copy, we only have to determine an appropriate multicast group so that we can replicate the packet to all next hops within this configured port cluster in one shot without recirculation. How do we do that? First, we configure all combinations of ports within configured port clusters as static multicast groups. We do that to gain some robustness against changes in the multicast tree, for example, when an BFER joins or leaves. And then we apply the same logic as before. We have a combined FBM of the static multicast group, which indicates all BFERs that are reachable through this group, or rather through the ports that are part of this static multicast group. Again, we apply the ternary match operation on the beer bit string and the complement of the CFBM. When the match is 0, we know that the multicast group contains all ports that are required to serve the beer packet. We again order the table according to the size of the static multicast group, so we get the most precise multicast group, so we do not send replication to ports that do not need a packet. And when we now have configured multicast groups, configured port clusters of size n, then we need 2 to the power of n static multicast groups because we have all combinations. And for our previous example with 32 ports and our 3 port clusters of size 11, 11, and 10, we need around 5,120 static multicast groups, and this is well feasible on a device like the Intel Tofino. We implemented this approach. It runs at 100 gigabit per second per port on the Intel Tofino. Next slide, please. This approach can be further optimized as follows. Next slide, please. We have certain assumptions about multicast traffic. We believe that multicast traffic is not completely random. We mean by that there is some correlation on egress ports. So there are certain port combinations that tend to occur together, and other port combinations are less likely to be used for a single beer packet. And the second assumption is that we only have a limited number of static multicast groups, so we have to comply to a certain maximum number that we want to use. And our optimization idea is now the following. We sample beer packets locally. Based on the beer bit string, we know which ports have to be used locally on the device to forward the beer packet. This information is stored in a graph structure. And then we can apply clustering methods to choose appropriate configured port clusters, such in a way such that all of them together cover all ports of the switch, and that ports that statistically occur more likely together in a beer packet have to be used together are in the same configured port cluster, so that we can use a single multicast group to serve all of them. In the end, this means that we need less configured port clusters per beer packet on average, and this reduces the required number of recirculations. Next slide, please. Here's a small example. When we get beer traffic with around 4.5 next hops on average, in our old implementation, this required 3.5 recirculations on average, which is the red bar in the graphic here. And in our new approach with the optimization, when we have highly correlated multicast traffic, which means that there's a high correlation between egress ports on beer packets, then we need almost 0 recirculations with around 1,000 static multicast groups. That's the bar on the right. And when we have less correlated multicast traffic, which means that there's some randomness within the use of egress ports for beer packets, then we still need around a single recirculation with 1,000 static multicast groups instead of the 3.5 recirculations in our old approach. Next slide, please. So to conclude this talk, we presented a mechanism to forward beer traffic with only a few iterations instead of the number of next hops. And to that end, we choose so-called configured port clusters and then apply an iterative processing, where in each iteration, we select a configured port cluster that needs a packet copy, and then we send a packet to all required ports within this configured port cluster in one shot. The second step may be achieved through predefined internal multicast groups, as in the case with Intel Tofino. However, these multicast groups are static. They are not dynamic, so we do not need any dynamic state. And this may also be done differently depending on the technology. So when there's another replication mechanism that is more efficient than multicast groups, this can be also used. With this mechanism, we have a maximum number of iterations, which is bounded by the maximum number of port clusters, for example, 3 instead of 32. And we can even further optimize this approach by packet sampling and then applying machine learning to get appropriate configured port clusters. We implemented this at line rate at Intel Tofino, and more details can be found in our paper here at the preprint, which is currently under review. And we are happy to discuss any questions. However, we have to see how this will work when I don't hear you. Thank you.
Okay, so Stefan, can you hear us or no? Oh, okay, so excellent. Questions? Nothing on the queue? All right, so I would have, yeah, Greg?
I said nothing remote and nothing in the room.
So I have one question. The rest was pretty clear. When I look at the picture, why is the orange and the blue overlapping here? Is there any rhyme or reason to that stuff?
Because maybe there are certain multicast groups or certain number of beer packets that have a subset in the yellow cluster, configured port cluster, but there are also some beer packets that need ports of the second one. And as we configure all possible combinations of ports, when we have disjoint configured port clusters, we need at least one recirculation when we need to have a packet that needs ports of both clusters. And when we can do overlapping clusters, then there's the chance that we need no recirculation at all.
Okay, so basically you had enough ports and you chose the sizes that way, but they do not have to overlap, right? You have both possibilities, just no optimization.
Exactly.
Okay.
Again, yeah.
We got one question. So is that Sandy? No, it's Jeffrey at the mic. Go ahead, Jeffrey.
From Juniper. So if I understand this correctly, each cluster is kind of like a line card on some routers. Another thing, so inside each cluster, it seems that you may be doing like a bit string lookup on the entirety, or just on the bits for that cluster only. And both ideas have been documented, or in some scenarios, in some companies' internal implementations. We can discuss further offline. And additionally, I guess it's really depending on the implementation. I know that some implementation do not require a recirculation for each iteration of the lookup that bit in the bit string. So indeed, I guess for some hardware, each iteration does require recirculation, and in that case, this optimization will help.
Yeah, definitely. So we are a bit limited in the number of table lookups that we can do in P4 and on the Tofino. So we do not have a way to make 30 lookups in one iteration, for example. So we have to do these recirculations. And this is a way to optimize how we do these recirculations. But I'm really interested in more information about the line card capabilities of existing beer implementations.
All right, Guyan.
Yes. Can you hear me?
Yes, we can.
Yeah, I just had a quick question. You know, on the so P4, I think one of the major advantages of P4 does help with the pipeline programming and staging, the ability to eliminate recirculation that happens on the ASIC. You know, by doing just the recirculate, you know, the programming with P4, are you able to eliminate the pipelining or eliminate recirculation? I think have you tried without having to deal with the randomness? I think like you had to in your one of your last slides you mentioned that you're working on how to the optimization. So if you without the optimization and if you just strictly did everything just with P4 and with the pipeline programming, were you able to get to a point where you can eliminate recirculation without having the optimization? Thank you.
Well, yeah, thank you. Thank you for the question. Of course, you could do it all without recirculation by just copying the packet to each egress port that has a potential receiver, and then dropping the packet in the egress when the receiver is not needed. But in this way, you will block the egress port. So when you get 100 gig and each port has a receiver at the end, and we make a packet copy to each port, then the whole switch is full and we cannot have any other traffic. That's why we need a way to determine before we put the packet in the egress ports, which egress port needs a copy. This is quite difficult in P4 based on the header length of the beer bit string. And at least we did not find a more efficient way as we just presented here.
Thank you.
Okay, one more question from me because I'm thinking about the stuff more and more. So when you did the static multicast group calculation, it seems low to me. So is the static multicast group per cluster? So can you assign basically the same multicast group in terms of an address twice for each cluster, and that's how you're counting it? So you reuse basically multicast addresses, or are they all unique across all the clusters?
It's not a multicast address. It's an internal way of telling the Tofino to do a packet replication to certain ports. And basically we tell in the control plane, give us a multicast group for these ports, then we get a number. And based on this number, we can later tell the Tofino to replicate the packet to these ports. And we have up to 2 to the power of 16 multicast groups available on the Tofino. And on our example, on one of the slides with these 3 configured port clusters, we used 5,000 of them. So that's why we have.
But what you're showing here is really that the identifier is unique across the clusters, right? Okay, yeah.
Across all clusters. So
yeah. Okay.
Yeah.
I have a question. So when you say internal multicast group, these are actually group addresses like IPv4 multicast addressing is built into the structure of Tofino, or what do you mean?
No, it's a 16-bit number, which is called multicast group on the Tofino because it behaves like a multicast group as it replicates packets.
So
but
it's
it has nothing to do
index
with
table to a
groups.
Gotcha. So an index table pointing to a group of output ports.
Yeah.
Thank you.
Okay, so basically when you try to do 2 clusters, you ran out of those identifier size.
No, so this is for all clusters.
Mm-hmm.
But yeah, when in the 32 port switch, we cannot have only 2 clusters with each 16 ports because we only have 2 to the power of 16 exactly.
Okay, cool. Yeah, that was what I was kind of aiming at. Thank you. Yeah, very clear. Any more questions, observations? Yeah, super work. Thanks. Most interesting. Toles, may we?
All right. So I had this earlier version, I think 2 years ago. So be back here now. Next slide.
Coming.
Okay, so
we continue to think that traffic engineering is really very important, right? So we've got BIER-TE out. We're getting back a DetNet to all the good things where we could actually, for multicast, use BIER-TE. And I'm not going to read through the long list. I think most people hopefully should know them. And then through working through BIER-TE, I think we got to the point where I was happy if it was working in small scale, and then everybody was asking me about large scale and make it larger and everything. And so then, you know, the ideas came around on what the root cause of the problem is. And it's really what I would call now the flat bit strings, right? So BIER-TE was designed to be as much as possible using the same hardware forwarding as BIER, which means one single flat bit string. And now we think that we can do better when we are taking into account that we're 10 years after the original BIER design. Our hardware forwarding planes hopefully can do better. And we think that we can encode trees more efficient than BIER-TE, make larger headers easier to process, and make it easier to auto configure. Next slide. And this is, by the way, highly experimental, right? So this is by far not, hey, here is a new great solution, everything is done, but we're at the end of a longer road. So on the right-hand side, what you're seeing is the multicast tree that we want to send a packet over. And instead of having a flat bit string, we're now encoding into the address field of the packet for each forwarding router a separate bit string. And then we're ultimately setting up the tree that way. And what we're doing is that the serialized encoding is updated on every hop, so that the hop that is processing it only needs to look at its own bit string, and then for every copy that it does, it is simply updating the offset and the length to point to the downstream neighbors, what we call recursive unit, which is the bit string, and then of course all the downstream neighbors bit strings themselves. Next slide. This is, of course, very high level. Here's the encoding and the processing on every hop. So you see on the upper row, you see the processing on router A, which would be the root. And the root, of course, sees the whole tree. The first bit string on the left, BSA, is the bit string for the root. In this case, it is making two copies, one to router B, one for router C. To do that, it examines only its own bit string. Then for the serialization, we need to have the length of the subtrees for B and C. One is actually derived from reading the RU lengths.
So let's very quickly, before you kind of lose everyone in the room, possibly me as well. But you describe only trees which have maximum fan out of 2, right?
No. This is arbitrarily many. So in this case, we're just showing 2 bits. So it can be many bits, and the AF field is an array.
Okay.
Right? So there would be, okay. Maybe I should have an example with 2. 2 AF entries.
All clear. Thanks.
Yeah. So this is an array, and we're saving one array element because we can calculate the length of the last recursive unit. Because we can take the global RU length field and do the calculation that is in that field. So obviously, you know, this takes longer than the fast slide deck. Hopefully the visuals are somewhat helpful, but yeah, I think we'll take more time to breathe in. But the main point is every router only needs to look at its own bit string, and that bit string only needs to have as many bits as that router has interfaces, so to speak, or host neighbors. Next slide. Right, so this is a little bit different view of the same thing, right? Obviously, this could replace the bit string field of an RFC 8296 packet header. And then the cost of the serialization, right? We love the fact that we only got every router's bit string that we need, not the bit strings from any router where the tree doesn't go through. But the cost, of course, are exactly these addressing fields that are telling us the length of the subtrees and then the global RU length and RU offset. So this is kind of the overhead for the savings that we get. Next slide. And so we did some simulation, some calculation for large scale networks. So this is, I think, Beijing Mobile in China with a couple of hops, right? So every hop is individually in there. And then this comparison, actually not even against BIER-TE, but against BIER. And the total number of replication needed to reach a certain random subset of receivers and then going through all possible random subset of receivers, starting from a small number, going to a very large number. So, and of course, these type of simulation, these type of analysis, we need more from to actually vet than the scalability benefit of this mechanism. Next slide.
So there's a lot of very small writing, but I see that you basically achieved it even with the very small bit mask size of 256 bits, the whole simulation, correct?
That's yeah. So I haven't been able to validate this. This is what my colleagues in Beijing have done, right? So obviously, the more we get into that assessment, the more we'll have to revisit these numbers and look for different topologies as well. Yep. Next slide.
Okay.
Okay, so the three big things, right? So replication efficiency for small trees in large networks, right? So, and it's easier to make the comparison with BIER because BIER-TE with all these different optimizations it's very difficult, right? Imagine you have a network with 10,000 BFER and you've just got a bit string length of 256, right? So even replication to a small set of 10, 20, 30, or 40 random destinations on the large network, right? Across that network may require up to 40 packet copies in BIER and BIER-TE because they're all in different bit strings, right? So you have 256 bits, so that's 40 different bit strings. So even for small trees, you may need a large number of copies, right? And so why do we care about small trees and large networks? Well, that's what we did, started in 1994, right? Which we called it PIM sparse mode, right? We want to have efficient delivery, small trees in large networks, and that hasn't changed just because we want to go stateless. So that's why small trees are actually quite interesting. Next slide. So then we had this fun discussion with Dino. He isn't even here. So that was basically, I was trying to be really provocative, and that's the red warning, offensive technology, right?
Congratulations, nothing new. Keep on.
Right. So consider really, why don't we have bit strings that are, 10,000 bits long, right? What's bad about it? So, and then go through the reason why it does or does not work, right? So in the first place, I think it would work perfectly fine from the benefit side. Okay, it's 1 kilobyte worth of bit strings, 1 kilobyte worth of data, but we still only have an overhead of 50%. We're sending it to a large number of bits, 10,000 receivers, and we have an overhead of 2 times, right? If we do ingress replication, it's an overhead of 10,000, or right? So if we go PIM sparse mode, sure, we only have an overhead of 1, but then all, the stateful operation. So why didn't we like large headers up so far? I don't think the MTU is the issue, right? 1,000 byte more MTU. If we start with data center, I've worked with so many crazy networks with really, gigantic packet sizes, right? I don't even think it is long-term the accessibility of the header, right? We've started with header from 128 byte. Now we're at 512 byte. Would say we can access 1 kilobyte of header in the forwarding plane in 10 years. But the problem that we have is we don't want to process 10,000 bits worth of stuff when we only need to replicate to 10 outgoing interfaces, right? If we only want to replicate to 10 outgoing interfaces, we should only have to look and process something that is proportional to the number of replications we really can do. And that is exactly what RBS gives us, right? We're only looking always at a local bit string, and all the other header is just payload that some other router down the tree will look into. Next slide.
Pushed it on more. I think we jammed.
Okay.
No, here.
So auto configuration, right? So I mean, I started BIER-TE. I'm not really a fan of centralized controllers, right? I love traffic engineering, but I would love to have, as lightweight as possible traffic engineering in the source router, in the first hop router, doing explicit source route. And I don't want to have to configure new address spaces on every node. And with this mechanism, RBS, we really only need to have every router locally assigning a number from 1 to 20 for all the 20 bits of its interfaces, and don't have to have global address space like the BIFT ID that we need to do, BFR ID that we need to do now in BIER and BIER-TE to basically split up the identifiers of routers across the different SI, right? So that problem goes away. And I think we could, with this mechanism, also get back to something that is a lot more, if not fully auto-configuring. So next slide. Yeah, so scale, right? That primarily comes because we're not doing this hard subdivision into fixed 256 bit strings or larger, right? So we are not wasting any bits that we're having in the bit strings, just, you know, the overhead of this tying together, the auto configuration. And then I'm starting to become a big fan of really looking into strict hop by hop source routing because that eliminates all my IGP problems that I may have along the path, like IGP micro loops and others, right? I can basically take all the updates out of the hardware forwarding table on the midpoints. The only stuff I need to do is my big ingress router with a big CPU is creating my, you know, hop by hop source routing header in the data center, and the hardware routers doing the replication along the path never need to update hardware forwarding tables. Next slide.
Sorry, flip to something else. Yeah.
Right. So we're looking for interest, feedback, collaboration, right? Is this easy enough packet processing? Obviously, you know, we have the plus, we have the minus. We want to continue evaluating and improving the approach, scalability, comparison, implementation, feasibility, such as in P4. You saw one of the co-authors being Michael, right? So we're working on that together. And then, of course, there may be other proposals that are looking beyond the flat bit strings that we've done and that hopefully we're starting to successfully deploy for the next generation beyond that, right? And then ultimately, you know, when we feel that we have something that enough people feel could work, right? What are the criteria that would make any such non-flat bit string solutions acceptable as a BIER working group, right? Obviously, rechartering, we had to do that all the time, but what are the criteria, right? What are the bounds of what BIER ultimately would want to do? I'm not asking to answer that question now, but I think it would be really good to have an answer, you know, within the next half a year or a year so that we know where to put what work, because the more we get working group support and people interested, I think the better the result will be.
Okay, we got a queue filled up here. I'm just going to give you comments first from the chat. From Edward V saying MTU is, I think he meant smaller problem. Much bigger problem is how big header ASICs may process. It may be as low as 128 bytes.
Right. If that is as low as it's get on those type of devices, then we have to see what's the best use in that, right? So I'm not sure if we could claim that this is better than a flat bit string. You've seen we've done the comparison for 256 bits, which is by itself less than 128 byte, but of course we also have other header overhead. So yeah, let's do the comparison there as well, of course.
All right, next participant, Zhang.
Jeffrey Zhang from Juniper. So when BIER-TE was first brought up, I was not believing it. I was in doubts because I didn't see it would scale. But when this RBS was brought up, I liked it, and I can clearly see the advantage compared to BIER-TE. So this is a good thing. There are some benefits on the slides. You claimed I will need to understand it better, but the basic idea of using recursive structure and to save the bit, the overhead using local bit precision, that's the key. It does work and I like it. One suggestion in the name itself, to me, it's really just BIER RBS. Don't call it CGM2.
Oh no, the CGM2 I already removed. That was basically the overall architecture, and that is kind of controller, local controller, so that's already gone. Yep. Good.
All right, Tony.
Okay, so speaking purely as participant, okay. I like that. I'm surprised by these 256 bits that the result is so good. So, you know, trust is good. I would like to see that verified independently. Yes. Because the gains are impressive. It looks simple enough to process in hardware. There are, of course, open things like how do you make sure that everybody computes the same tree? What will happen while the tree is converging, like loop prevention, right? The usual discussions, what will happen there? Nothing, because each node has to kind of see the same tree and know the offset, who is the next node. Maybe I'm missing stuff, but it's just this thing that I'm thinking like network has to be converged state for the whole thing to work, methinks. I wouldn't even call it TE2. This will be a fundamentally different way to process the bit mask. Yeah, me likes. Okay, that's what I can say. I think it's a great proposal if the numbers and you know these little things that we don't see to work out. And yeah, okay.
My biggest challenge, of course, is so we've done an evaluation, of course, in actual hardware, which is like everybody else here, vendor proprietary hardware that researchers can't verify. So that's why Michael is doing it on P4. If P4 has problems, I'm not sure how much that is going to tell us, right? So the decisions of what is actually feasible everywhere, I think in our space is really a difficult one to do. And I hope that we can all try to do that, as good as possible.
Yeah, but the number of replication can be actually, and the gains in number of replication can be simulated here. I mean, you don't really need the hardware implementation here.
No, I think it is about the complexity of the calculation that you need to do to update the two fields and extract the information, right? So the packet header processing.
That I would kind of abstract that looked like a fairly simple hardware operation, comparatively speaking. Not as simple as ending bit mask and so on, but it doesn't look like excessive TLB processing to me.
Full disclosure, this is the upstream marketing presentation. Read the draft. There are details, right? So let's.
Yeah, I will. I will. It triggered it. I mean, I didn't have time to read the draft, but you triggered my interest definitely.
Yeah, I see. So yeah, I also find it a very nifty approach. So it's quite nice. Although, so I send my comments to the list.
Oh yeah, sure. No, those are two very valid. I just didn't have the time. I need to do next breath with those feedback.
Yeah, because I think there's some design choices made to not put the more state in the packet, but put it in the control plane where it doesn't belong. So I do expect actually the header size to increase if you want to solve that problem. Yeah. So the data that you're showing here for these 256 bits might not be as good as it looked today.
Yes. Yeah, definitely.
Okay.
But which goes back to the part, what are the overall benefits and does the total header size really as opposed to the processing cost, right? So let's distinguish those maybe.
Yeah, no, but I definitely support looking into this more, for sure.
Yeah. Yes, just a few comments. So I really like the idea. It seems like an optimization. It kind of takes some of what exists today, I guess, in ideas of optimization, and it seems like a good improvement, and works with, as you said, small trees are important, versus big trees, but it really is a real nice optimization to BIER. One initial idea, I guess, a comment. Could this, since it does use the architecture and idea of using a bit string, could this actually be like an extension or possibly an optimization to existing BIER architecture? Thank you.
Yeah, I mean, I described how it would fit into an 80-96 header, right? So obviously we only have power of 2 length of the bit string right now. So we would need to do some padding, and ultimately we could use all the different lengths depending if the hardware does it, right? So yeah, it could be fit in there. Is it the best header? But I don't think we can save a lot by trying to optimize that header just for, saving every single bit.
Well, I mean, so there was a strong architectural and practical consideration to put the bit mask at the very end, right? So hence, I mean, the power of 2 is artifact because the algorithms to look up, right. So good, but there is nothing that will, put a crimp into our whole thing if we make the bit mask different length. So, we'll have to think how to encode it. In terms of the BIER encoding that we have today, we have a version on it. We can always bump it to version 2, or we can think of how we semantically distinguish, just like with the BIER-TE, how do we semantically interpret the bit mask differently? So I don't think architecturally anything would prevent us to go and have yet another semantic interpretation of the bit mask and all the existing hardware, right?
Yeah, the simple way to do it is have different subdomain semantics, like we also defined for BRTE. That's what I have in this slide.
Absolutely
Whatever it is, yeah.
possible. I mean, the control plane, we can go wild, right? So that we can synchronize who assigns which semantics, to what kind of bitmaps, as long in the hardware we don't start to pile stuff up. So yeah, fundamentally, I don't see like architecturally that wouldn't fit in the encodings we have and the architectural degrees of freedoms that we provided. Yeah.
Makes sense. I like it. Thank you.
All right, so we way over time. I think the other things are not earth-shattering, pretty much these updates. All right, I have to find my window again. Yeah. Here we are. So what else is on the thing? We still have the BFRR update. Yeah, we can run through it quickly. I mean, otherwise people can just, fade out.
Hello, everyone. I'm going to talk about BFRR. Will be very quick. Basically, I would thank all the people who give comments and suggestions. I think we address all the comments and accept all the suggestions. For example, I think Jeffrey Zhang suggested that we should have one forwarding table and then for BFR and the normal forwarding. So we added one extended forwarding table for normal forwarding and for FR. So in addition to that, and then some people mentioned that what's the relationship between BFR and IPFR. So we addressed that. Next page. So this is the structure of one forwarding table for all. So basically it contains primary entry and then backup entry. And then we'll have flags indicate whether this backup entry will be used. Next page. So regarding to BFR and IPFR, so one question is that we already have IPFR. Why do we need a BFR? So this is because BF package is forwarded without IP header, outside header. So in this case, IPFR cannot apply to the BF package because BF package doesn't have IP out headers. So in this case, when one BIER next hop failed or unreachable, and then BIER package will be dropped and then lost. So that's why we need BFR. So regarding to BIER LFA and IP LFA, so basically BIER LFA will use IP LFA as much as possible. So when we have IP LFA, whether in some system, in the IP forwarding table, whatever. So if that one, the LFA is also the BFR label node, and then we can directly use that IP LFA. So for IP LFA, we have different types. We have basic IP LFA, and we have remote one, and we have topology independent LFA. So those three types will also reused because we have a architecture to support normal action, which is just forwarding the package to the next hop. And then we also have a tunnel, and then we have also explicit path. So all these are covered. So next page. So we just want to welcome more comments and suggestions.
Yeah, Human Goldie, Nokia. I mean, yeah, great idea, but I'm still scratching my head. Usually the deployments that we've seen with BIER, unicast is enabled. So most of the deployments, they want to follow unicast. So I'm still kind of scratching my head. Why do I want to separate my BIER fast reroute from unicast?
So BIER, so what I got a question is that you mean we don't need this one? don't need a BFR?
No, sorry. So going back to your slide, you had 3 different of fast rerouting. So if you have basic LFA,
oh yeah,
you don't need the
remote and the
well, if you have basic LFA and your fast reroute can be resolved via basic LFA without remote or TI LFA, then you just use the beer header, right? You push it to the fast reroute next hop, and then the beer header just follows the IGP. My only point here is that beer advertisement is via IGP anyway, so it is in the mercy of the IGP. And what we have realized, I mean, our implementation is you just turn on LFA in the network, and beer just follows it. There's nothing special about it. That's how the like even from implementation point of view, we didn't have to do much. You just turn on the LFA under your IGP, and beer just follows it.
Just follow IGP. As long as the IGP have one, I think normally it's okay, but sometimes because some nodes don't support beer, in that case we may have an issue. If every node support that one, it's okay. Yeah, every IP LFA is also BF LFA, and then we'll WhatsApp. No problem, right?
Yeah, again, maybe you want to bring up the cases. I mean, again, we haven't seen any case that the IGP LFA cannot resolve, but maybe bring on the cases and we can discuss.
Yeah. If all support, then that's okay. We just follow IP LFA.
So jumping quickly in, I mean, we had kind of this discussion, ongoing discussion, but to keep everybody open-minded, right? Yes, today we deploy the IGP with slave to our unicast, all works like a charm, but fundamentally, architecturally, we're not slave to IGP, right? We can run completely different computation, build completely forwarding table, install via controllers. If we're not slave to IGP and IGP-FRR is not good enough, this has the architectural degree of freedom, which arguably we don't need today in deployment. Okay, but there's nothing fundamentally wrong with the work that is completely useless because we assume we always have an IGP or we always follow unicast. Okay.
Well, okay. Again, I just want to be very careful here. Even with the controller, like if you have SR policy or anything that comes down with the controller, again, from what we see from the implementation, it just follows what is installed in the data path, right? I mean, we don't see anything specific, but yeah, I mean, I'll take it back. If there is something specific that we are trying to solve here, which we haven't thought about it, yeah, for sure. I'm just giving a feedback to the working group that, based on the live implementation and live deployment, this is what we are seeing.
Okay, I mean, this discussion has been going, that was the first comment given to the draft. Okay, so thanks for the update.
Okay, thank you.
Right. Something else chasing me, but it's okay. And we come to the very last one. And we way over time, okay?
Okay, can you hear me?
Yeah, Sandy, loud and clear.
Okay. I'd like to say this is a very simple draft. It is used for BRTE, BP, a BIFT ID advertisement in BRTE in circulation. Sorry, because the previous slides, the previous draft is not are not optimal. So we'd like to use a new advertisement for the BIFT ID advertisement. So the only change for the new draft is that we move the BIFT ID advertisement from the BP to the prefix. So we just only advertise the BIFT ID once. So this can reduce the advertisement bytes consumption greatly. Yeah, that's very simple. Oh, sorry. Please, next. So we know that the this is for the BRTE, which is defined in APC 9262. So it's used for the BIFT ID advertisement. Next. So we know that we must advertise the BIFT ID for the BRTE table. routing table lookup. So you need to advertise the BIEFT IT. Next, please. So the previous structure is advertise the advertisement in previous structure is advertise the BIEFT ID under BP, the TLV. So we just move the operation to the prefix, so the advertisement may be more efficient. So the BIEFT ID is allocated per SD BSL.
Ladies and gentlemen, hard stop. We're being kicked out the room, justifyingly so. We overran mercilessly. All right, Sandy, sorry, we pushed the stuff to the next session. Thank you, everyone. Interesting session.
Thank you.
Tony's got to pay for beer for everybody tonight.
Sorry, guys. We have to clean out the room. We have to clean out the room. Yes. After next, man. First, we have to clean out the room.